I'm running it for 300 iterations. Basically, this is how many iterations it is going through a region growth process. I found 300 to work for this. It depends on your seeds, how many of them there are, and how big your volume is, how many iterations you're going to need, and also the dilation bias. The dilation bias determines how the tendency of the algorithm to go outside or inside of the border of the feature that you are trying to segment. I found that 0.17 gave me a fairly good volume for this particular image. This may need to be adjusted based on your image contrast, your image features, and yeah, so I found that you may need to play with this a little bit depending on the specific features of your image. And then down here, I am simply displaying the image, which is how you get this picture. Next, I cleaned up the binary volume a bit because, as you can see, there's a few floating volumes here and things that are not attached to the main volume of the vessel, and we want to get rid of those because that will they're not useful. So what I've done here is I've generated just a slice through the center of the volume, and I'm using the BW select function within MATLAB, and this will pop up with an image just like this. And you can select points within your main vessel. And so what I've done is I've selected a point here and here within my main vessel. And in these lines here, what I'm doing is I'm just generating a list of coordinates that are within these voxels that I selected, and using the BW select 3 function that will select any voxels that are directly connected to these voxels that I selected. And so we're not going to get any floating bits of volume. We're only going to get parts of vessel that are directly connected to these selected voxels. What I'm doing here with the imclose function is I'm just closing up any holes that might have been generated within the desired volume. This is specifically for the centerline extraction process, because if there's any holes, it can cause problems with the MATLAB centerline function, but also just you don't want any weird one voxel holes within your volume, because that can cause problems down the line. And so this will close any of those holes. And then finally, displaying this cleaned up volume. It looks very nice. As you can see, there's no floating bits of volume. All we have are our connected vessels here. Then finally, the centerline extraction. We use a process called skeletonization. And so this is going to be using the BW scale function. It's very nice, very useful. You just import your volume. Mine is called V2, which is basically just your binary volume that I have displayed here. And you set the minimum branch length. And so I've set mine to 15 voxels. This can change, obviously, depending on your image resolution and your specific geometries. I've set mine to 15 and it worked quite well. And yeah, as you can see, the center line of the image is displayed in this picture here. And yeah, so that's what we're going to be exporting. So finally, exporting the binary image stack. So this is going to be for our segmented image. What I've done here in this first line is create a folder called PNG bin. In the next line, what I'm doing is I'm converting my binary volume into a 16-bit image stack. And so I'm converting it to a uint16, which is basically each voxel is going to have a value between 0 and 255. And then I'm multiplying it by 255. So each voxel is going to either be 0 or 255. And so it'll be black or white. And then for each slice of my desired image volume, I'm creating a file name, including the directory path, the folder, PNG bin. I'm reusing the file names from the DICOM images, which typically will be something like im0001, and then I'm adding a .png at the end, so it's going to be im000001.png, and then I'm using the imWrite function to write one slice of my image to this file name, and then I'm repeating that for each of the images. So im0001, im0002, and so on and so forth. Now here, what I've done is I'm using the find function to determine the coordinates of each of the 1 values for my center line, which is my scale matrix. However, there's no function within MATLAB to find 3-dimensional coordinates, and so what the find function will do for a 3-dimensional matrix is it will find the row, but within the column, within the column vector, it will have basically it contains the information for the y and the z coordinates. And so what I've done is I've taken the mod of the column to get the z coordinate, and then the floor division of the column to get the y coordinate. And then I've brought them all together in this coordinates matrix. Here I'm opening a file to write the coordinates to. This is the file name, and then the W denotes that I'm writing to it. And then for each line of coordinates, I'm going to write X, Y, Z, and continue for the entire list of coordinates, and then close my file. And closing the file is very important so that it doesn't get corrupted when the program finishes. And that is it for my method. Thank you so much for listening. Please feel free to check out any of our other instructional videos on the PM3 channel. And don't forget to leave a like and subscribe. Thank you very much.